Good day, viewers. Welcome to Cayman Physics tutorial. Um, in today's video, I'm going to be teaching you a very simple skill or secret. Um, Previously, on my last video, I started teaching you guys dimensional analysis, and my last video, I taught you how to check if a formula is dimensionally consistent, if a formula is dimensionally correct. However, for a formula to be dimensionally consistent doesn't mean that the formula is scientifically proven or this formula is scientifically correct. Scientifically correct is different from dimensionally correct, right? So those are two different things. So I don't want you guys to mix it together. So if you have not watched the last video that I posted, I will encourage you to go to any of my channel. You can go on YouTube to Cayman Physics Tutorial. That is the name you are seeing here. Cayman Physics Tutorial on YouTube or on Facebook. Cayman Physics Tutorial on Facebook as well. Like on YouTube, you can press the notification button so that when I drop videos, you can be notified. Invite your folks, invite everyone, invite your family, everyone in high school, college. They should come and learn physics. Yeah, physics is really very, very, very interesting. Right. So today I'm going to be showing you a secret. Same on dimensional analysis. So what I'm going to be doing today is I'm going to be showing you guys how to get the units of a particular constant in physics. It's very hard for us to be cramming units. The unit of some constant, like the first one I have here, the gravitational constant. This is the first one I have. This is the second one, and this is the third one. So to get the dimension is very easy. Then when you get the dimension, you can find the units. You can't keep cramming what is the gravitational constant. You know the value, right? You know the value, but you have to put the units. So students usually face the difficulty when they are writing exams and they want to use a particular constant. They will remember the constant, but to remember the units, they won't remember the units so easily, right? So in this video, I'm going to be showing you the secret. I'm going to be revealing the secret to you guys on how to get the units of any constants, any physics constants, by just finding the dimension. Then from the dimension, before you know it, you are already getting the units of that particular constant, right? So stay with me on this video, like, share as I continue on this video. Today, I'm going to show you guys how this is what we are doing today. How to find the units of physics constants in physics. Very easy, and just stay tuned and follow me on. Right, so as you can see, I have 3 questions here to find, which is the first one is you are asked to find the dimensions here, but from the dimension we are going to obtain the units. From the dimension we are going to get the units of each of these, right? So let me take the first one first and solve it for you so you guys can see how it looks, how to solve that. Right, so I have it here. This is the first question I'm going to be solving now. Right, so here we are asked to find the dimensions of the universal gravitational constant, which we all know as capital G, right? So we all know it as capital G. So before you can start, you need to know what the formula is. Like I said in my last video, if you have not watched it, go back and watch it so that you can know what we are doing here, right? The current stage we are right now. So you need to know the formula. Once you know the formula, then you can proceed. We know that in this particular gravitational force constant, this is like there's a particular law that actually holds these constants. We call it Newton's law of gravitation, right? So you need to know that. Once you know that, then we can proceed from there. So we can say from Newton's law of gravitation, right? We all know that from that Newton law of gravitation, you know that we always have like two masses, right? Which one is probably m1, the second one m2, right? Then we say that there is always a force of attraction or repulsion between these two masses on Earth, which we always use the distance between them as r, right? The distance between them is r. Then we say the force of attraction between these two masses, m1 and m2, separated by a distance r, is directly proportional to a particular force as well, right? So the combined formula is something like this. The force of attraction is F, which we always say is directly proportional to the first mass, right? And the second mass, m1 and m2, right? So you guys know the next thing, which is going to be the distance apart, the r. The r is not directly proportional to the force of attraction. The force of attraction or repulsion is inversely proportional to the inverse of the square of the distance apart. To the inverse of the square of the distance apart. So if you join these two together, you are going to have F directly proportional to m1, m2 all over r square. This is just variation. Then from there, you can have something like F being equals to, when the proportion sign goes, when this proportion sign goes away, what is going to come in? A constant is going to be introduced, right? A constant will be introduced, which let's take as k for now. So m1, m2 all over r squared, right? So the k has been shown to be a capital G. It has been taken as capital G. Scientifically, it has been proven. We represent it as capital G, right? Which we all have been using, and we have the constant. The constant has also been proven scientifically, right? We just want to show how to find the unit of that G. So if we take that k as G, which is the gravitational constant that we are actually universal gravitational constant that we're actually trying to find the unit, then you can say F is G m1 m2 then all over r squared. Then this is going to be our formula that we are going to work with, right? This is going to be what we are going to work with. This is going to be our formula. So don't forget, we need to make G the subject of the formula, right? Whenever you are looking for the units, you don't need to start deriving the formula out. Once you know the formula, just jump to this particular stage. Just jump to this stage. Once you know the formula, jump to this stage. You don't need to waste time. Then from there, once you jump to that stage, you can make a G that we are looking for. You can make the G. The G is the concentration here. You can make that G the subject of the relation. You can make that G the subject of the formula. Then, if you want to do that, the G, that is good. If you cross multiply from here, definitely F r square is going to give us G m1 m2, right? And then finally the G is going to give us F r square all over m1, m2. Let me write it afresh. Means that G that we are looking for is F house squared all over m1 and m2. Right? So this is going to be the formula that we are going to be working with, right? So you know what the unit of force is, but now we are looking for the dimension. So you find the dimension of each of these quantity. You just quickly find the dimension of whatever the quantity is. For example, we are going to take F. We are going to take F first. The F here is force, which is very easy to take as hem A. We all know that is hem A, right? In my previous video, I have shown you guys that the hem is capital hem, which is the mass. Then the A is the acceleration, which we have proved as LT minus 2, right? So in a way, we can say the F will give us hem LT minus 2. Right. In a way, we can say this, that this is what we are going to have as for the force. Right. So the next one here is, the next thing to find here is let's look for the R, and then we look for hem. So to find the R here is the distance apart, right? And what is distance? R here is distance. The distance R, of course, that's going to be length, which is going to be capital L. The dimension is going to be this, right? That is going to be what we are going to be having for the dimension, right? So, and then that is what the dimension will be. And the last one, which is the mass as well, hem will be the mass, which that will still be the capital hem as well. So now, in short, we have been able to get the three parameters that are there, which is the F, R, and the hem, right? The F, R, and the hem. So once you have gotten those three things, you can now come back and substitute into this formula. Then you apply. Whenever you are seeing square, you can put the square. So the G now will now be close to finding the dimension of that G. So if you recall, we say G, if you go up, you see what G is, F house squared over hem1, hem2. So let's put it now. So if you substitute all of those things in it, it means that the G is going to give us mLT minus 2 for the force. Then we have L for that radius. There is a square there, so don't forget the square. Then we have two masses here. The two masses is going to take m. The second one we also take hem. That is hem squared, right? So if we proceed from there, the G will give us mLT minus 2 multiplied by L squared all over hem squared, right? So we can do some elimination from there and eliminate whatever we are seeing at the top and whatever we are seeing at the bottom, right? So we can say this, we are still going to be left with one hem, right? So it does means that the G, in terms of hem LT, right? So that means it's going to give us, we have L here, L square and L, both can come together to give us L raised to power 3, right? So both can come together to give us L raised to power 3. So from there, we can just decide to say that the G will give us L cube now, the L times L square. Then we have the T, which is raised to power minus 2. Then the M here is at the bottom. So when we bring it up, it becomes par. So if you want to rearrange that very well, you can say that G the dimension for G will be m per m L raised to power 3 C raised to power minus 2. Right? So that is what you are going to be having for, that's what you are going to be having for the dimension of this. That's what you are going to be having as the dimension. Right? So that is the dimension. But we are not looking for the dimension. We are looking for the units. Right? So, and don't forget, I told you in the first video, if you have not watched that video, go and watch that video. I told you that we usually have every fundamental quantity, the 7 fundamental or basic quantities that we have, they are 7. And for all of those 7 quantities, we usually have their specific dimension, and we usually have their specific units. Now you have gotten the dimension. You just change the dimension to units. You just change the dimension to units, right? So changing the dimension to units is not something that should be hard. If you see hem here, that is like mass is going to be in kg, right? If you see the length, right, is going to be in meters. Then if you see the time, is going to be in seconds. So whatever parameters you have on it, you can replace it back. So at the end of the day, my G can be in per kilogram, right? You put the -1 back, meter cube, right? Per second squared. That is what you are going to have. That's what you are going to have as your answer. This is what you are going to have. You can see it's very easy. Once you get to this formula, once you get here, once you are able to get this, what is our F? What is the formula that I want to find? Here you are looking for the G, right? Then you make the G the subject of the formula. Then when you are done, you look for the dimensions first. You look for the dimension of each of the parameters you are seeing here, each of the quantities. So when you get all of those ones, you just slot them back into the G. And then you break it down until you have just one single L, one single T, and one single M. Then you can turn it back. We know that anywhere we are saying the mass, the unit is kilogram. The unit of the time is seconds, and this is in meters, right? So you just replace it back there, and you are going to be left with the units. Very simple, right? So if you realize that we have 3 questions here, I'm just going to solve another one for you guys. Then I will leave the third one. I'm not going to solve these for you guys, right? I won't solve that. I'm going to leave you guys with that, but I'm going to solve the second one now, so that you guys can see how that is being done. All right, so let me go to solve the second one for you guys. That deals with viscosity that we are looking for the units. They ask us to find the dimension, but we are going to be going ahead to find the units of that particular quantity, right? So that is the next one that we are going to solve. If you look at this carefully, the way I solved the first one, you will see that it's very difficult for you to put this in your head, right? It's difficult for you to put this in your head. Like you a lot of quantities where we have in physics. Why should I put the unit for coefficient of viscosity? So, but it's easy to find, very easy to approach, very easy to find, right? You all remember what coefficient of viscosity, how it came in, right? There is always a force, right? There is a law. That law is called Newton's law of viscosity. That is the second question. From Newton's right? From Newton's law of viscosity, there is a formula that joins this coefficient of viscosity out, right? The formula says that there's a particular force, which is the viscous force, F, which is a viscous force, if you remember. So like I said, you need to know the formula. Then the formula also says that we also have a particular area, A, which is the distance between the two layers of the liquid. Capital A, which is the area between the two layers of that liquid, right? So the next one, other parameters that we also have there is the Hertz. That is the change in the separation between the two layers. That is the Hertz, which we usually use as separation between the two layers. Separation between the two layers, right? Then the last one is the dV. The dV, we usually have the V there, which we all know that V is the velocity, right? So that is the velocity difference between them. That is the velocity difference between them. You can see this D means change. The D I'm putting between them is the change. That is the velocity difference. The velocity difference between the two layers as well, right? So knowing all of these things, you can come ahead, you can, by now, as I'm writing all of these things, those of you that you are very, very vast with physics, you ought to have think of a formula that relates viscous force, area between the two layers, the separation between the two layers, then the velocity difference. You should have been getting the formula by now, which says that the F, the viscous force, is directly proportional to the area, right? Is directly proportional to the area, and that same viscous force, right, is directly proportional again to the change in the velocity difference, right? And then that same viscous force is inversely proportional to the separation between the two layers, which is what I have represented as the hex. Those are the three things. You will just join those three things together and you are good to go. So join those three things together. If you join those together, you are right. So if we join those first together, it's going to give us F directly proportional to the first one, which is A, directly proportional to dV, and inversely proportional to the hex. Of course, that's going to give us something as F directly proportional to A. Then we can write this as dV over dx. So in some way, you can also, in physics, we usually call something like this velocity gradient. Don't forget, velocity gradient. But that's not where I'm going to today. We usually call that the velocity gradient. That's what we call that. Velocity gradient. Right. So dv dx, which is the velocity. Like I said, this is the velocity gradient. So this is the formula, and you know when the proportionality signs goes away, what is the next thing that comes in? The constant will be introduced, right? So we can introduce a constant. Let's just call it k or anything. So therefore, the F is going to give us k a dv over dx. I've defined all of these things for you, but the k has been proven again, such as we proved the k was changed to the g, Newton universal gravitational constant. This one also has been changed, and we call it eta. It's a Greek symbol. We have taken, it has been proven that the k is taken as eta, which is a Greek eta. So that is what we use for the k. So if you rewrite that, you are going to have that F to give us eta a dv over dx. So that is what you are going to have. This is what you are going to have. Right? So from here now, this is what I'm working with. You can see the formula now is set. The same way you are going to have that eta is taken. Don't forget what that eta means. That eta is the coefficient of the viscosity that you are looking for. Let me put it here. The eta is the coefficient of viscosity. Right? So that is what that eta means. So don't forget, you don't need to start proving the formula like this. I just want to remind you, and that is why I'm doing this. If in exam you are expected to know this formula already, you just jump here, right? You just remember that the force is directly, viscous force is directly proportional to the area between the two layers, and also directly proportional to the velocity between those two layers, and then inversely proportional to the separation between those two layers, to the separation. Or sometimes we say the force is directly proportional to the area and directly proportional to the velocity gradient, as short as that. So once you know that, you can proceed, right? Once you know that, you can proceed and you are good to go, right? So that is going to push us forward to making that coefficient of viscosity the subject of the relation. That is the same thing we did the last time, right? So if you make that one the subject of the relation, that eta is going to give us f dx, if you do that, all over a dv. This is what you are going to have. This is what you are going to have. Right, this is what you are going to have. So you know what we are looking for. We want to find the dimensions of each of these things first, but finding the dimension will not be hard, because once you have been following me, you should be able to find this dimension without having to know the formula, right? If you recall, I'm just going to recall all of the dimensions for you guys quickly. The viscous force, whether viscous force, whether classical force, whether dynamic force, whatever force, whether it's a pull force, a kinetic force, whatever type of force, the dimension will always remain. That is MLT minus 2. Don't forget, right? So MLT minus 2 is what we are going to have there. Then for the hex, it's just the hex means change. Just the D there means change, right? So whether we are going to have this whether we are going to have this as change, or you want to have it as S, the change doesn't really matter if you are writing, because I'm sure you'll be thinking, oh, how do we want to solve the change? The change there doesn't really matter. It just talks about, it's just a physical interpretation of what we will be doing, right? It doesn't really affect the dimension. So the L is still L, which is the length, is still what you have for that. The L, because it's still a length, right? Whether you say change of length or something, still a length, right? So the next one is the area, right? Very simple. That is going to give us length times breadth, or length times length, which will give us the length squared, right? So the last one is the velocity, which is that same dv. D doesn't really matter here as well. That's going to give us LT minus 1. Right, good. Now we are close. So you just substitute all of this back into that formula. Then you do the needful. So if you recall again, let me record that formula for you. Eta is equals to F dx all over A dv. Yeah, it's supposed to look like this. So that is what the formula is supposed to look like, right? So what next? The next thing now is for us to substitute. So if you substitute the dimensions, right, you are going to have eta to give us the first one first, MLT minus 2. Then the length for the hex, right, all divided by L squared, that is for the area. Then the last one is the velocity, which is LT minus 1, right? So here we can quickly do some elimination very fast. This can probably annul this. We can do some elimination. This can annul this. Then we'll be left with 1. Then what can annul again? This is t raised to power minus 1. When it goes up, we can compile it together so it won't confuse those in high school when you are watching this video. So as a matter of fact, you are going to be left with eta giving us m, right, t minus 2 at the top. Then the bottom is going to be L t minus 1 at the bottom, right? That's what you're going to be left with. The whole idea is that you should just pull this together. So as a matter of fact, if you take that up, eta is going to give us, you can start with m, right? You can just start with m. L goes up, it becomes L minus 1. Then you can join these together. That can actually give us something like, let's start with that's this, and this can be joined together, right? So and you have t minus 1 times t. When that one comes out, it becomes t, which is 1, right? The negative time we turn to a plus when it goes up, right? So we can close that, right? So if you join that together, very simple. We can just use indices for these two, right? So minus 2 and the time multiplication we turn to plus. We're going to have minus 2 plus 1, which is negative 1. So at the end of the day, we can have the dimension to be m L raised to power minus 1 t raised to power minus 1. Did you get that now? So that is how we are going to be solving that. Now we have the dimension. So the next thing now is the same way we have been doing it. You have the dimension already. Just make sure that all the masses is 1. The L is 1. The T that's been compressed, whether you multiply it, whether you apply indices. Most times in this type of operation, we apply indices. Just compress it. We don't want to have double M, so it won't be hard for you to change to their their units, right? So you remember again, once we have M, you know what we usually have, right? So for that one, this will give us kg, just to remind you again, this meters, right? And then this we turn to seconds. I have not put the powers on it, so you can now apply the powers. So if you apply all the power, that will be kilogram, right, per meter. We call this per meter per seconds. That is what the unit is going to give us. This is what the unit will give us, right? So you can see it's very, very simple. So like I said, this is going to be the final answer for that. If you want to call this together, you call this kilogram per meter per seconds. So like I said, you don't have to go through all this process if you want to solve it. The only thing to do is to remember this. Once you remember that, you know you are looking for, oh, I want to use coefficient of viscosity, and I know the formula for viscous force that connects the area, the velocity gradient together, and then the coefficient of viscosity as well. Come up with this formula immediately. Then you make eta that you are looking for the subject of the formula. Then all of these ones, you don't even have to write them out like this, right? I don't expect you to start writing it out. All these things, you should know this, you should know this, you should know this. Just substitute everything directly into this. Then compress together, and you are going to have the dimension. The dimension is the first thing to have. Then from the dimension, you are going to have the units, right? So I've solved the two questions for you. I'm going to show you the last question again, which I will be leaving to you guys to solve, right? I'm going to be leaving it to you guys to solve. This is the last question. Yeah, this is the last question that I want you guys to solve. So I need, if when you are done, I want to have comment from you guys. You guys should probably comment and show me your workings. Show me, if you can't show me your workings, just show me the final answer. Show me what you have done. If you can comment what the unit will be for this electrical permittivity. So the electrical permittivity, what is the relation? What does it relate to? So you guys should go and find out. Find out what this relation is, what is related to, what law governs this electrical permittivity in physics, and what do we call this particular symbol. This symbol you are seeing here, what do we usually call it? That symbol you are seeing here, what do we call it? So comment, share this video to everyone on YouTube. My on YouTube, my my name is the same. Go on YouTube, search for me and follow me. This is my information. Follow me on all of the social media platforms, especially YouTube. I drop videos 4 or 5 times in a week on YouTube. So go there, Cayman Physics Tutorial. Go on YouTube, search for the name, subscribe, and then click the bell such that when I upload the video, you'll be aware. It's going to automatically notify you. The same name I used for my Facebook, the same name for YouTube. Invite young folks, invite our youngsters to come learn physics so that we can enjoy the 21st century physics and modern day physics together. Right. Thank you guys. See you in our next class.